Hello and welcome back to the Science of Concrete Materials class. This is lecture number 27 of the class, and today we will start on a new module, which is the fresh properties of concrete. Okay, as mentioned, in this part of the class, we will talk about the concrete at early age. So the properties of fresh concrete are important, primarily because they affect the choice of equipment needed for handling and consolidation, and because also they may affect the properties of the hardened concrete. So there are two sets of criteria that we must consider when making concrete. First, short-term requirements while the concrete is still in the plastic state, which are generally lumped under the term workability. Second are the long-term requirements of the hardened concrete, such as strength, durability, and volume stability. As we will see when we study the proportion of concrete, as these two sets of requirements are not complementary, and a compromise is needed between them. Okay, so again, as we said, in this part of the course, we will study the short-term early age requirements, and of course we will study the remainder coming up in lectures. So these are really the concepts that will be introduced and discussed in this module. We're going to talk about the term workability. Related to it, the terms are segregation, bleeding, slump, and the slump test. We're going to talk about set-in time and testing of the set-in time. Other tests such as the air content and the various methods for measuring the air content, such as the gravimetric method, volumetric method, and the pressure method. We are going also to talk about the unit weight and yield and the plastic shrinkage. These are just generally the concepts that will be discussed. So just, to give more specifics, this is an overview of what's covered in the course. We're going to talk about workability, as I said, the factors affecting workability and how we measure workability. Setting, define the setting. Of course, we have been introduced to this term before, but in more related way to concrete, and the tests, how we test setting time for concrete. And we are going to talk about other tests performed on fresh concrete, the air content and the unit weight, and the early age deformation, which is the plastic shrinkage. Okay, so let us discuss workability. So again, from the standpoint of a finished product, for hardened concrete to be of an acceptable quality, for a given job, the fresh concrete must be capable of satisfying the following requirement. It must be easily mixed and transported. It must be uniform throughout a given batch and also between batches. It should have flow properties such that it is capable of filling completely the forms for which it was designed. It must have the ability to be compacted fully without an excessive amount of energy being applied. Easily compacted. It must not segregate during placing and consolidation. It must be capable of being finished properly, either against the form or by means of a traveling or other surface treatment. Okay, so let's define the term workability. So the aspects of the quality of a fresh concrete we just mentioned all have different requirements. So a number of terms are in common usage, each emphasizing different, facet of concrete behavior, such as, the terms you just heard: consistency, flowability, mobility, pumpability, compactability, finishability, and hardness. These terms are, both subjective and qualitative. So they mean different things to different people and are therefore not very useful when you talk about these terms. So here we use the term workability to represent all of the properties mentioned. To be a little more precise, let's define workability. Workability is often defined in terms of the amount of mechanical work or energy required to produce full compaction of concrete without segregation. Okay, so this is just a simple, brief definition that really encompass all of the terms we just mentioned above. Okay, this is a useful definition since the final strength of concrete is in large part a function of the amount of compaction. A small increase in void content or decrease in relative density will lead to large decrease in strength. If you recall the discussions during the microstructure properties relationship, we talked about how the increase in voids or the decrease in density will decrease the strength. Okay, so but we have to remember about workability. It is not a fundamental property of concrete. It is basically a function of conditions, equipment, type of concrete, the mix itself. So it's not a fundamental property of concrete. It is a qualitative property incorporating consistency, which is the ease of flow, and cohesiveness, which is the tendency to bleed or segregate. So that basically how you view workability. So let's look at what segregation and bleeding are. Segregation refers to the separation of components of fresh concrete, resulting basically in a non-uniform mix. So in general, this means some separation of the coarse aggregate from the mortar. This separation can be of two types: either the settling of the heavy particles to the bottom of the fresh concrete, or a separation of the coarse aggregate from the body of the concrete, generally due to improper placing or vibration. All right. Okay, although there are no quantitative tests for segregation, it can be seen quite clearly when it occurs. The factors that contribute to increased segregation are as follows. Remember we talked about the aggregate size. So larger maximum particle size, over 25 millimeters, and the proportion of large particles. This thing, affects segregation. A higher specific gravity of coarse aggregates as compared to the fine aggregates. If you remember, we said the specific gravity of the coarse and fine aggregate is in the same order, but if it happens that the specific gravity of the coarse aggregate is higher as compared to the fine aggregates, then we might face the problem of segregation. Also, a decreased amount of fines, the sand or cement. changes in the particle shape away from smooth, well-rounded particles to odd-shaped, rough particles. Finally, mixes that are either too wet or too dry also will increase the probability of segregations. So the use of finely divided mineral admixtures or entraining agents reduces the tendency towards segregation, but careful handling and placement methods, are more important than this factor. Okay, bleeding. Bleeding is defined as the upward movement of water after concrete has been consolidated, but before it has set. So the water being basically the lightest component segregates from the rest of the mix, and because of that, bleeding basically is a special form of segregation. So water on the surface of the concrete is the most common manifestation of bleeding. So bleeding generally caused by the fact that, as the aggregate particles settle within the mass of the fresh concrete, they are unable to hold all the mix in water. So some bleeding is normal, for good concrete. It results in a small amount of uniform seepage over the entire surface. That's, good bleeding. On the other hand, bleeding may occur through distinct localized channels, and small craters that, may form at the mouth of each channel, like in distinct channel. I'm sure you have seen it. It looks odd. So the upper layer of the concrete may become rich in cement paste, which has a higher water cement ratio than the rest of the concrete, which leads really to weakness, porosity, and lack of durability at the surface. Also, water pockets may form under large particles, aggregate particles. Okay, let me go back here. I don't know if you can see it here under the aggregate particles, like you see the shadow. Okay, and also under the reinforcing bars, basically leaving weak zones in the concrete under these particles and under the reinforcing bars. So if the bleed water evaporates more quickly than the bleeding rate, which is the case in hot, dry weather, plastic shrinkage will occur. So the concrete will bleed to the surface. So if the evaporation is too high, faster than the rate of the bleeding, then we will end up with plastic shrinkage. Also, as a manifestation of the bleeding, sometimes we get like a scum of fine particles that could be carried out to the surface of the concrete, basically creating a weak, non-durable surface. Or salts may crystallize at the surface, leading to the formation of the calcium carbonate, which is referred to as latents. If this occurs at the top of a lift, between successive lifts, poor bond to the next lift will be a result of that. So will be poor bonding between lifts. If on the other hand, if it occurs at the top of the flat slab, the surface will be prone to dusting. That is very dry, powdery layer that will appear on the surface of the hardened concrete. And this will be a permanent feature of the concrete. So deterioration will be a combination of the latents and the plastic shrinkage. So latents should always be removed by brushing and washing the surface, okay? So how we deal with bleeding? What can we do to reduce bleeding? Number of ways. First, by increasing the cement fineness, or by using pozzolans or other finely divided mineral admixtures. Also, by increasing the rate of hydration of the cement, like by using cement with high alkali contents or high C3A contents. However, this may have undesirable effects, as we said before, or by using accelerators such as calcium chloride, and again, this may have undesirable effects as well. Maybe also through the use of air entrainment, which is very effective in reducing bleeding, or by reducing the water content. If this can be done while, of course, maintaining acceptable workability. Basically, maybe the use, if we reduce the water content to overcome bleeding, the use of water reducers and plasticizers to maintain the certain level of workability we want. Okay, so bleeding or the bleeding capacity can be measured. So both the rate of bleeding and bleeding capacity can be measured using the procedures outlined in ASTM C232. The method involves consolidating a sample of concrete in a container with an inside diameter of 254 millimeters, 10 inches, and a height of 11 inches. The container is then covered to prevent evaporation. The bleed water rising to the surface is carefully drawn every 10 minutes for the first 40 minutes, and then every 30 minutes thereafter until bleeding has stopped. The total bleeding and the rate of bleeding then may be determined. Okay, but you have to be careful, two slightly different procedures, one for concrete consolidated by tamping, and one for concrete consolidated by vibration are outlined. These two types of consolidation will generally lead to different results. Okay, this method is out there, but using it, you have to be careful when you use it, as far as being consistent throughout the batches we're using it, and of course making sure you use the correct method as far as the consolidation or the whether you use consolidation by tamping or by vibration. Okay, so let's look at really the factors. What affects workability? The workability of concrete, as you have probably figured by now, are affected by a number of factors, like water content, of course, and the cement content as well, the mix proportions, the aggregate properties, which plays a big role, time and temperature, or basically the ambient conditions, characteristics of the cement itself, and the use of admixtures. All these affects workability. So almost everything affects workability. So how the water content of the mix affect workability? This is the single most important factor governing workability of concrete, which is the water content. Increasing the amount of water will increase the ease with which concrete flows and can be compacted. But apart from reducing the strength, increased water may lead to also segregation, which is the settling of the coarse aggregate, and also bleeding. So in general, any collection of particles require a certain amount of water to achieve a plasticity, so it can be worked. First there must be enough water to absorb on the particle surfaces. Then water must fill the spaces between the particles this additional water to lubricate the particles by separating them with a water film. Okay, so, and again, you're thinking the water has to do certain things before it becomes available for the workability of the mix. So from this, it follows that, the finer particles, which have higher specific surface area, require more water. Okay, so the finer particles have higher surface area. That means, based on the previous discussion, explanation here, it will require more water. On the other hand, without minimum quantity of fine material, the concrete cannot, exhibit any plasticity. So there should be a balance. So the water content of the mix cannot be considered in isolation from the aggregate grading. And you remember when we talked about aggregate, we touched upon this subject. So for optimum workability, finer aggregate grading require higher water contents. So again, there has to be a compromise and a balance between the fine aggregate content and the water content. Okay, so with regard to cement characteristics, though, it's known, that the cement characteristics are much less important in determining workability than, basically the aggregate properties. But the increased fineness, for example, of the type 3 high airless strength cement will reduce workability for, at a given water cement ratio, as, these cements basically have higher water requirements because of their higher specific surface area and because they also hydrate more rapidly. Remember when we talked about the cements? So it has been found, that if cement is delivered to the job hot, let's say above 100 degrees Celsius, there may be a considerable loss of workability, due to more rapid hydration and evaporation of water. In addition, at temperatures, higher than 60 to 80, flash set may occur. So be careful of that. Okay, so let's look at the influence of the aggregates. Basically, when considering the effect of the aggregates on workability, two factors are important: the amount of aggregate and the relative proportions of the fine and coarse aggregate. Okay, so for a constant water cement ratio, an increase in the aggregate to cement ratio will decrease workability. Also, more cement is needed when finer aggregate gradings are used. Okay, so a deficiency in fine aggregate results in a mix that is harsh, meaning prone to segregation and difficult to finish. So basically the harsh mix, if we remember the definition, harsh mix is one that lacks desired consistency because of a deficiency in mortar or aggregate fines. This is the harsh mix. On the other hand, though, an excess of fine aggregates, meaning over-sanded mix, will lead to rather more permeable and less economical concrete. Although the mixture is workable, but we have other issues to deal with. So, and again, we said the balance between the mixed proportions, the aggregate to cement and the aggregate itself. So just, to remember, it is not sufficiently merely just to look at the ratio of coarse to fine aggregates. Different sands will behave differently because of differences in particle size distribution. This is generally, expressed in terms of the fineness modulus, which we talked about during the aggregate module, if you remember. Also, the other factor, we talk about the shape and texture of the aggregate. So the shape and texture of the aggregate particles can also affect workability. As a general rule, the more nearly spherical the particles, the more workable the resulting concrete will be. Okay, the spherical particles will have lower surface to volume ratio, and less mortar will be needed to coat the particles, basically leaving more to provide workability, okay? And this is also partly, due to the fact that the spherical particles will act as ball bearings, as you can see in the figure here. While angular particles will have more mechanical interlock, and that will basically require more work to overcome the resultant internal friction, okay? So smoother particles provide better workability. So when flat or elongated particles, are contained in the coarse aggregate, the quantities of sand, cement, and water must be increased, okay? For obvious reasons, to overcome the interlocking effect. Also, the porosity of the aggregates may also affect workability. If the aggregate can absorb a great deal of water, that means less will be available to provide workability. So it may be necessary to distinguish between the total water content, which may include absorbed water, and the free water content, which is available to provide workability, and which basically determines the water cement ratio. We will talk about this concept during the mixed design lectures. Okay, so also the ambient conditions affect workability. So there is considerable evidence that as the ambient temperature increases, the workability decreases. We talked about this. As you can see here, I will talk about it in a minute. Since, higher temperature will basically increase both evaporation rate and the hydration rate. So this basically suggests that more water may have to be used in warm weather to maintain the same workability. Also, the quantity of water required to change the slump by some given amount increases as the temperature increases. All right? But on the other hand, there is also some evidence that, at least for short times, workability itself is not affected by the temperature. So you have to investigate both evidences. So so where temperature may be a factor, remember this, where temperature may be a factor, field tests should be carried out with the specific materials in order to determine the temperature effects for a given job. As I mentioned before, it's not really 100% consistent relationship about the temperature and the workability. So testing is definitely a key here. Okay. So again, also something more to mention about the relative humidity and wind. So lower relative humidity and exacerbated by windy conditions, evaporations occurs more quickly. That's something also to keep in mind. So this is the graph I was talking about, the effect between temperature and slump, and of course the effect is different for the different maximum aggregate size. You remember, the aggregate size is important to consider when looking at slump, and we talked about this during the aggregate lectures, if you remember. Anyway, but this one just shows the general trend for both sizes, that with the increase in temperature, the slump basically decreases. That's the general trend. Okay, also admixtures, definitely, as we have mostly, looked at during the lectures on admixtures, both mineral and chemical admixtures. So with chemical admixtures, like air entraining, water reducing, and or set retardant admixtures will all improve the workability. But there's a big but here, but that you have to remember. It should be noted that, chemical admixtures react differently with different cements and aggregates, and can, in some circumstances, aggravate the loss of workability. So in particular, when using high quantities of super plasticizer, which is required for some high performance concrete mixes. So the problem, of cement plasticizer compatibility must be addressed. And again, trial mixes on the same material you are using for that particular job. So because since, we cannot yet, predict exactly how a given super plasticizer will react with a particular cement. So this must be done empirically through laboratory and field tests, trial tests. There is no other way. As we said, also mineral admixtures are, often used to supply additional fine material to harsh mixes. When they are used simply to replace, part of the cement, they may have little effect on workability. But if they are used to provide basically fines to the mix, it's a different story. Okay, so let's see how we measure workability. As you can see here, there's the most common test. I'm sure most of you are familiar with the slump test. But generally, as can be reduced, the term workability is applied to a number of different properties of fresh concrete, that are affected by a large number of factors, as we have seen. So it has been, suggested that workability should measure at least 3 separate concrete properties. 1, compactability, which is the ease with which concrete can be compacted and air voids removed. Mobility, which is the ease with which concrete can flow into forms, around steel and can be molded. Stability, which is the ability for concrete to remain stable, coherent, homogeneous mass during handling and vibration without the constituents segregated. So basically, excuse me, that's what the workability or the test for workability should basically look at, or at least contain within its parameters to measure. There are a large number of workability tests, have been proposed over the years. Almost all of them are, completely empirical. Only few of these, not one, few of them have been incorporated into standards. The rest have received very limited use. So we have to keep in mind that none of the available standardized tests measures workability in terms of fundamental properties of fresh concrete. Okay, none. So also, these tests are single point tests, and therefore cannot be expected basically to describe the properties of a material such concrete. You take the slump test, for example, at the point of discharge from the transit mixer to the pump, or maybe sometimes at the other end after it's being pumped to the location where it's being placed. So it cannot really, this does not encompass, all the properties of the materials of concrete with just this one test. Okay. So the available tests, cannot even easily be compared to one another also, since they tend to actually measure somewhat different properties of the concrete. That's also something to keep in mind. So in in any way, it is important to have some measure of workability of concrete. So basically, until some better test, procedures are developed, we must make use of one or more of the available tests. So most of the available methods do at least provide information as to the variations and workability for a given mix, and are therefore useful as quality control measure and to ensure consistency. So again, we are not looking for exact values, we're looking for consistency. So the slump test, for example, is a good quality control measure to verify uniformity and consistency for a mix, within batches or between different batches. Okay. It also has to be noted that none of the available test methods can be used over the whole range, very wet to very dry concretes. All right. So an individual test method can only be used over a relatively low range of workabilities. You cannot use these different test methods. They basically, as I will show in a coming up slide, they're used for different types mixes. So the different measures of workability that have been developed over the years are, like slump test. We have the compaction test, the flow test, and the weep test. I'm going to focus on the slump test though, in most of my discussion. So the slump test is by far the oldest and most widely used test of workability. It first appeared as an ASTM standard back in 1922. Now it is described in ASTM C143. The apparatus for this test, is very simple, and basically consists of a hollow mold in the form of a frustrum of a cone, as you can see. Right here, it's in here, and shows the shape of it and the dimensions. The mold basically is filled in 3 layers, and each layer is rodded 25 times with a 16 millimeter diameter steel rod. After that, after the top layer is stricken off, the mold is lifted away vertically and the slump is measured, as you can see here. No, I went too far. Let me go back. This is a slide here. Okay. So the maximum time from the first placement of concrete to lifting of the cone is 2.5 minutes. Also, if a distinct shearing off of concrete from one side of the concrete occurs, then the test is regarded and a new test is carried out. What I mean by shearing off, something like this. Okay, if such shearing off occurs consistently, this indicates that this test is not suitable for this particular mix. I mean, we have to use another test to basically measure workability. Okay, so the slump test may be, again, considered to be a measure of the shear resistance of concrete to flowing under its own weight. Of course, this is the shape of the concrete molded inside, and basically it's a resistance to its shearing off, or the shear resistance to hold its shape. So depending on the mix, we might get 3 distinct types of slump, or 3 types of slump that may occur, as shown here, A, B, and C. So we have in A something called the true slump. Basically consists of general subsidence of the mass without any breaking up. As you can see, just general subsidence from the top here without breaking up. We have also the shear, which I just talked about, the shear slump. This one often indicates lack of cohesion. It tends, basically to occur in harsh mixes or in mixes prone to segregation. The shear slump also may indicate that the concrete is not suitable for placement. So again, when you get shear slump, flags should go up. I mean, alarm will sound when I see shear slump, which is not often, by the way, just to be fair. But right away you should be alert. Okay, so that means it's not suitable for replacement. Or as I said, normal mixes sometimes found to display shear slump, and again you have to repeat the test or look into the more specifics of the mix to make sure it is suitable. We have also the collapse slump. Generally indicates basically a lean, a harsh, or more likely a very wet mix. So remember that many modern high performance concretes, which are specially designed for a slump about 200 mm, which is 2 inches, display basically this type of slump behavior. Okay, and again, you should have an idea. If you are an engineer on the job or a foreman checking the slump, first of all, you should be that the engineer should coach the foreman, or the quality control staff should be aware of what to expect on this mix from from an experienced person. Any variations of extremes right away should be flagged to the supervisors in order to take appropriate actions. Do not overlook these variations, which could be of disastrous results. Always bring it up to your supervisor just to make sure whatever concrete is coming to your job site is suitable for replacement. Okay, so more about slump. There are a number of difficulties associated with the slump test. The test is completely empirical, and as I said, is not related to our earlier definition of workability, which basically, as I said, the definition of workability, which involved the measure of the amount of energy required to compact concrete. Okay, so with different aggregates or mixed proportions, the same slump can be measured for different concrete consistencies. And again, I mean, the concrete we measure, it's a quality control tool, measure consistency, but again, does not really measure fundamental properties of concrete. For example, as you can see in this slide here, I know it's probably not very clear, but I will explain. Basically, as you can see, here's the slumped concrete. Here's after the cone has been lifted, and here's the slumped concrete, and the measure is almost the same. So each one of the top and bottom, if you, for example, if they are tamped, lightly on their side with the rod, see what happens to this one and to that one. This, tells us more, about, and gives us more information about workability. The upper concrete basically is a very harsh mix with a minimum of fines and water. So the lower concrete is plastic and cohesive. So clearly these two concretes could not both be used for the same purpose, although we have the same slump. Okay, so in addition, the slump test cannot differentiate between low workability concretes, which may all give no slump, or concretes with the slumps less than 25 mm. So concretes with slumps less than 25 mm should be tested by another procedure, preferably one involving vibration, since vibration will be needed to consolidate basically such stiff concrete. Although the test is, like I said, reasonably reproducible with a skilled operator, it's quite sensitive to variation in test procedure, and it is not uncommon for different operators to achieve values by more than 25 mm, 1 inch apart for the same concrete. Okay, so as indicated earlier when describing the workability time relationship, the slump may vary considerably depending on how long after mixing the test is carried out. All right. So again, many limitations, many variables, and really these tests will require the person to have some skill and knowledge and some experience when to make a judgment about slump when evaluating a slump test result. Anyway, in spite really of these limitations, the slump tests can provide useful information to us. In general, concrete of similar slump can be used the same way. More important, the slump test is a valuable quality control tool, as I said. Okay, so changes in slump on a given job generally indicate a change has occurred in the aggregates or in the amount of water or admixture being used. So this should provide a warning that something is happening to the mix so that the remedial action can be taken if necessary. And again, we are looking for consistency and uniformity. All right. So you must, like I said, you must be careful when evaluating the slump test results. An experienced person really should run the test in terms, not experience meaning filling the rod, experience to evaluate the test results and be able to either make a decision on accepting, rejecting the concrete, or at least to escalate the issue to their supervisor to make the decision. So anyway, any changes almost are always indicative of something that has been changed and attention is required. Okay, so here are the other really measurement methodologies of measurement of workabilities. This is based on the BS 1881. It shows here the workability range and the methodology. Like if we have very low, we use the VP time, the low, the VP time or the compacting factor, medium, compacting factor or slump, high, basically compacting factor, a slump or a flow. The very high, of course, we use the flow, we do not use the slump. Like for the high performance concrete mixes or for self-leveling concrete, for example, we do not measure slump, we measure something called basically flow. Okay, I'm going to stop here for now. So this will be the end of lecture 27, and we will continue next time with the topic shown here, the loss of workability. So until then, thank you for watching and see you next time.